see. Yeah, maybe it's time to start. It's a great pleasure for me to introduce Christof Weitenberg. He's a good friend of ours, and we know him since probably almost a decade or more. Christof is a professor at the Technical University Dortmund in Germany, where he's starting out his own group now, but he already has got a long history in science with fantastic results. He got his PhD in physics in 2011 from the Ludwig Maximilian University in Munich for research that he did at the Max Planck Institute in Garching. And for those of you who don't know, the Max Planck Society is kind of like the top-tier elite society in Germany. And the Max Planck Institute in Munich has done a lot of pioneering work for ultracold atoms. So he was actually in the group of Immanuel Bloch, I think. And he was,
yes.
And he was doing pioneering work on single atom resolved imaging and single spin addressing in an atomic mod insulator. So the idea is that you fill a lattice, an optical lattice, with one atom per lattice site, and you can really detect one atom per each site. So this is really on the quantum level. Then on 2011 to 2013, he went to Paris, to the Laboratoire Castres-Bruxelles at the ENS, École Normale Supérieure, where he was working in the group of Jean Ladibard. And this is also one of the powerhouses in the field of ultracold atoms. And then from 2013 to 2024, he was a senior scientist, which is a permanent position. It's something which we don't really have an equivalent of here in Hamburg, where he was the group leader of 2 experimental teams, also in ultracold atoms, under the supervision or under the umbrella of Professor Klaus Sengstack over there. And I think since last year, right? Since 2024,
yeah.
he is at the Technical University in Dortmund. So his research focuses on ultracold atoms, optical lattices, quantum many-body systems, Fluctuation engineering, topological quantum matter, anyons. He is leading a research program on simulating anyons with ultracold atoms, quantum computing, machine learning, and quantum physics. So a lot of topics that are also highly relevant for groups over here. And he has got a rich history in outstanding publications, actually 33 articles, including articles in Science and in Nature Physics and in PRX and PRL and all those. And recently he has done some very interesting work from quantum microscopes and being able to detect the phase of little atoms on different sites. So we're very excited that he is here and that he can tell us about this new research. Please.
Yeah, thank you very much for the kind introduction and for inviting me to give this colloquium. And I think this is a very interesting format to exchange even without this very long trip that it would be. So good morning to you. It's evening here. Yeah. Okay, so let me share my slides. Shouldn't forget that. So can you see my slides?
Yeah.
Yes, looks good.
Great. And now I have this laser pointer. Yeah, so good. So I was asked to also give a short introduction to cold atoms. So I have 3 slides on that, and then I will talk about our most recent work, and you find all the details of that also in this preprint. And I will appear later again. So as an introduction to cold neutral atoms, what is that? We use gases of neutral atoms in a vacuum chamber, well isolated from the environment, and cool it down to the regime of really nanokelvin. That is done in 2 steps. First, we use laser cooling to go into the microkelvin regime in so-called magneto-optical traps. We can trap and cool the atoms at the same time. And while we do that, they are fluorescing. So that gives an image like you see here, where you have a cloud of lithium atoms in the center of the glass cell that you see here. Lithium is nice. You have this nice red color. Yeah. And then we switch off all resonant lights because that limits temperature to the recoil temperature, and go far below that by evaporative cooling. So always removing the hottest atoms such that we come to the regime of quantum degeneracy. And then now it depends on what kind of atom you use, what kind of species. So whether you have an even odd number of components of the atom. So we work currently with lithium-7, which is a boson. So then we obtain a Bose-Einstein condensate where all atoms go into the same quantum state, already at a finite temperature. Or if we work with system 6, we get a Fermi C to a Fermi degenerate gas. That's basically in a nutshell what we do. Of course, it's quite a complex experiment with filling 2 optical tables to get all the laser systems. And then one can do different things with it. What we mostly do is work with optical lattices. So we just use single frequency lasers and overlap them such that they interfere and form standing waves, such as you see here. So when you make such a 2D lattice, you get an array of tubes. And in our case, we fill them with bosons, so little Bose-Einstein condensates on each tubes, such that this forms an array of Josephson junctions with a spacing of just half a micron. So there's really tunnel coupling between the lattice sites. Or one can add another pair of laser beams, such that one has a 3-dimensional optical lattice, where then one has typically just 1 atom per side. And this can then be mapped to the Hubbard model. So this is really in the regime of Hubbard models, just filling the lowest band, just having on-site interactions. If 2 atoms are on the same side, that's naturally given at this ultra-cold temperatures. And then, of course, having a significant tunnel coupling. So, but all of this on a scale of just 10 nanokelvins or so. And this is a very pure realization of such Hubbard models, and therefore a good way to study them. And that's also something I've worked a lot of that, but today I will mainly focus on this regime of Josephson junctions. So one driving force for doing these experiments is quantum simulation. So the idea to overcome this exponential scaling of Hilbert space that we have scaling with atom number or with particle number, which makes it intractable to numerically simulate quantum systems. And then there is this idea to just simulate one quantum system with another well-controlled quantum system. So this idea then goes back to Richard Feynman and is nowadays realized, for example, with ultra-cold atoms. Nowadays, we have indeed the control over quantum system to do this. And one famous example is indeed using cold atoms in optical lattices and to simulate solids or electrons in a solid. So the atoms move on a lattice just like electrons do in a solid state system, described by the same Hubbard model, basically. And of course, this system is much simpler, so you can then find out which kind of physics in the rich phenomenology of solid state physics might be described by what kind of model already. And the 2D Fermi Hubbard model is already so complicated, you cannot solve it exactly. So one of the questions is what happens away from half filling. This is something one can try to answer with cold atoms. And another motivation for using this is that not only you have a very clean system, but also you have new detection possibilities that you don't have in a solid. For example, taking these kind of snapshots with a quantum gas microscope, where you can really detect every single individual particle of the many-body system in a projective measurement. So this is not a mean density, an average density of a scanning microscope or so, but this is really making, like projecting out one image and then freezing in one particular instance of the fluctuations. And from many of these images, you can have access to all kinds of correlations. So that's also a very important motivation here for working with these kind of systems. That was my short introduction. Are there questions about that?
Is there any way to get phase information between sites, individual sites?
Excellent question, because this is what my talk will be about. So let me just jump into that. So how can we access phases and coherences in a microscope?
Yeah,
so
maybe to emphasize one point. So in the previous picture, like each one of these blue dots would be one atom, right?
Yes.
Okay, so this is really single atoms on a lattice site image there.
Yeah. And so, yeah, I didn't really explain it well. And then they overlap with lattice to illustrate that. So you really see them, they're always lining with this grid. And you see there's not an atom at every side. And this is because this was a fermionic system with quantum magnetism. So with 2 spin states, and there's spin correlations. In this case, antiferromagnetic spin correlation. So this is actually in the Fermi-Hubbard model. And here they made some spin-dependent imaging by removing one of the spin states prior to imaging. So you only see basically the spin-up atoms here, and the empty sites correspond to spin-down atoms. And therefore, this checkerboard between empty and filled side that you see is actually a sign of the antiferromagnetic ordering in the lattice. That is directly visible here then. Yeah. Okay, so this is an image here from the Greiner group, 2016, but this technique is a few years older, so that was one of the things that we did during my thesis to develop this kind of imaging technique. Okay, so but now this is a very good question, because so here you can do a lot with that, but everything is in the occupational basis. Basically, you always see is there an atom or not, but you don't have access to phases. This is still very powerful because you can have access to all kind of multi-point correlators as well, not just two-point correlations. And this is, of course, was found out to be extremely important to really understanding this Fermi-Hubbard model away from half-filling, where higher order correlations are basically the decisive thing to understand what happens. But so let's still ask, what about phases? Can we also directly image phases? And this is something that is not routinely done, like on the scale of single sites. And so, but we recently did something in the direction. I'd like to present that and present two ways of doing it. One are Talbot revivals, and the other is this genuine phase microscope, where, of course, we don't measure the phase directly, but we map phase fluctuations to density fluctuations and then measure that, but in such a clean way that we clearly have phase information. That's basically what you always do, isn't it? You take make an interference and then see the phase via the density or something. So the Talbot effect, let me remind you of that. You've probably heard of it. It's the effect that happens in a near field. If you have a coherent field, say, if you illuminate a grating with light, you'll have revivals of these grating structures right behind this grating. That was already found in 1936 by Scotsman Mr. Talbot. And so then you can define the Talbot length, like at what distance this occurs, and it's given by the grating squared and the laser wavelength. And there's also a matter wave analogous of this effect, which is called matter wave or temporal time Talbot effect, because now it's evolution in time that dictates it. So we define a Talbot time that's also given by the square of the lattice constant and the mass in this case. And for our lithium atoms, this is 13.2 microseconds. So that's the time until we get here this full revival. Then we also have secondary revivals in between, where you also get a lattice, but just shifted to where we had the antinodes before. Because this is just the interference of near field interference, which gives rise to this effect, okay? In the case of a coherent system. And there is already some history of looking at this. So already in the 90s, people looked at the matter wave Talbot effect, back then still with atomic beams and material gratings, and scanning through one of them with a piezo, you would then see a varying contrast, which is a direct indication of this Talbot effect. And then later it was also done with optical lattices instead of the material gratings, but still with atomic beams. And then even later also with trapped BECs and lattices. And so this was just demonstrating that there is a matter of analogon. But then the next question is, if it is something that occurs in a coherent system, can't we use this effect to study the coherence of the matter wave? And there are three examples here given. So this is all with also with bosons. So where we have a BEC, a really coherent matter wave field in an optical lattice. And if you switch off the lattice for a certain time and then measure whether it's a revival, you get a measure of the coherence. So in this case, it was done by looking at a Bragg signal, kind of would there be a Bragg diffraction from the cloud, which is the case if you have this the density that is modulated, and that is something that would occur for a shallow lattice, as shown here in black. You would have this Bragg scattering with the revivals, kind of a revival time here of 60 microseconds in that case. And if you make the lattice deeper, as you see here, that vanishes. So then you don't have the Talbot effect because your original system lost its coherence. And a much more thorough study of that was then later presented in Kaiserslautern in Germany, here by the Ott group, where they had a 1D lattice, switched it off, switched it back on after a certain time, stepping through here in microseconds. And then by reloading into the lattice, they would check if the image, this Talbot revival would form. Whenever you had Talbot revival, you reload into the lattice, like suddenly switching it on, you would not heat because you have exactly the right density that was the ground state of this lattice. And then they looked here at the heating, so at the cloud width, and all these minima is where you had this revival. And then these maxima are basically anti-revivals, this secondary revivals. And you see here there's a really lot of revivals, yeah, because you have coherence over many lattice sites that then contribute to this large or late revivals here. And it was also done in 3D, so in a 1D lattice with direct imaging, yeah, where you can really see now that the contrast comes back here, but it also kind of gets more fluctuations. That's because here they used a very large lattice period to see that, where the tunneling is really suppressed such that it had basically a thermal gas in here. So, and that what we are now doing is basically also to directly image it, but we have a very good microscope such that we can do that in a lattice with just half a micron spacing, such that we have really a fully coherent systems to start with. And so how can we do that? That we image this very well, although it's so small. This is the so-called meta-wave microscope or quantum gas magnifier, what we also called it. So we you find a lot of details if you're interested in this technique in this article, and particularly in the supplementary material of that article, we wrote down all the technical details. But the fundamental idea is really quite easy. You just use harmonic traps as a meta-wave lens to make a Fourier optic. So you start with a density distribution, a lattice in our case, of atoms. Then you switch off everything except for a harmonic trap. And also, you know, in a non-interacting picture, so you just have the single particle picture of atoms oscillating in a harmonic trap. And after a quarter period, an initial displacement will have totally transformed to momentum. Yeah? And after another quarter period, back to position. And if you now switch the trap to be more shallow, just in this middle, so doing that, switch the trap and doing that, you're back to momentum, but now magnified. Yeah, that's basic idea that's shown here. This is just what the total density would look like. And in the middle, you have Fourier space. So for a lattice, that would be these Bragg peaks that you see here. So to get a magnification, of course, you have to change the trap here, and then you get this magnified image. And one can show that this also works well if you just completely switch off the second trap and have a free expansion that makes it easier to realize. And then the magnification is about given by the first trapping period frequency times this expansion time. And in this experiments here, we reached magnifications up to 90, which makes it then very easy to observe, to image this optically subsequently, even with moderate resolution that we only had available in this machine. And you see here that we really resolve very well this honeycomb lattice. So the spacing between these sites is only 400 nanometers, but it's still very well resolved. Let me also emphasize this work here by Selin Joachim in Heidelberg, who uses similar techniques in a regime of few atoms, and recently had a nice article here where he describes also a lot of technical details with fermions. So why is this interesting? It gives us a very high effective resolution down to 100 nanometers currently, but one can push it much further. So much better than optical resolution, which would be rather limited to, say, 600 nanometers or so. And it gives also large depth of focus, because we are not limited by optical diffraction or optical depth of focus, such that we can work with 3D systems. And indeed, this here is an image of an array of tubes with hundreds of atoms per side. which extend over 20 micrometers or so out of this plane. So optically imaging it would be completely blurred due to that, but now after the magnification, there's no problem. Yeah. Also, large densities are allowed. So again, these large atom numbers are not a problem because we dilute it. And so it gives us access to a regime that would be inaccessible without this technique. And yeah, is there a question?
Yeah. You talked about the what effect for the phase coherence, the Trotter? Wait, who was it? What? Anyways, how does that compare with the way Reiner et al. Measured coherence in their 2002 paper?
But I didn't talk about how we measure coherence yet. I just introduced this microscope. Yeah, so maybe I'll explain that after I tell you how we measure the coherence.
Okay.
Yeah. So, I mean, Greiner has a traditional microscope where he just uses a very high resolution objective to resolve the lattice sites just well enough to decide whether there's an atom per side or not. But that would not be sufficient to resolve a honeycomb lattice, for example. Okay. Okay, so so we do this now with the other machine, with lithium. We have also such images. And the advantage is that we now work with we have a Feschbach, so we do this trap now optically. So actually doing this well is not so easy. You need a very harmonic trap in order to avoid aberrations, and the trap has to be large because you magnify, yeah, and then still don't want aberrations. So in this other experiment, we did it with a magnetic trap. Now we switch to an optical trap because we want to use the magnetic Feschbach resonance to control the interactions. And that's important because we want to switch them off during this protocol of this matter wave magnification, such that we can keep the coherence. So actually in these images, we froze out the coherence prior to imaging, which is okay if you just want to see the density. But now if you want to study coherence properties, of course, we cannot do it. And the point is, as you see here, you have these tightly sharp peaks here in Fourier space if you have coherence. And this give rise to a lot of strong interaction effects that blur the images. So either you get rid of that or you switch off the interactions. And that's what we are doing now. And for that, we switched to lithium, where you have a Feschbach resonance in order to do so. And this is our latest work. But now the point is, if you have coherence, you will have this Talbot effect. So, which also you could see as an annoyance, because it's really hard to find out which is the right image and to time everything and be sure everything is aligned. It was a lot of work, but now we have everything under control, and that's great fun. And so we can also now nicely map out this Talbot effect in our 2D lattice, which is also new, was done only in 1D so far. So if we get the right timing to get a matter wave image, you have images like this. And if you wait a little longer in this first harmonic trap, so which is kind of adding a bit of evolution time before this matter wave protocol, before this magnification, then first the image blurs, but afterward it reappears with the secondary revival. That is the thing where the lattice was shifted. And in the case of a two-dimensional triangular lattice, the shifted lattice is actually an inverted lattice that looks like a honeycomb lattice. That's kind of what you expect. But so it makes it easy to distinguish it. Yeah. And then it blurs again and comes back as a first primary revival. And of course, we go even further and just monitor the contrast of these pictures. And this is the actual image where you have a large contrast, lattice contrast. This was the first secondary revival, the first primary revival for this image. But if we go further, we have further revivals. And we also get revivals for negative times, so waiting negative, like subtracting a time from the actual protocol, so that we have now a very broad region to scan. So in total, 14 revivals. Okay. So now we want to study coherence properties as a function of lattice depth. So for shallow lattices, we have large tunnel couplings and low temperatures. And if we increase the lattice depth, the temperature increases, tunnel coupling goes down, and at some point, the system becomes thermal. And that's a phase transition that seems to be around here, as you see. So a lot of things happen. This is the lattice depth. We plot here the contrast, and this is the evolution time. So what I just showed you was one slice like that. Yeah. So this was the actual image, and these were the copies, the revivals. You see that it shifts a bit, and this is due to some residual interaction effects because we still have a finite interaction. And you see the image branch that continues here, but the other branches then stop here where we lose the coherence of the system. Yeah. So we can, so this is the lattice contrast along these three lines, and you can now clearly say there is phase transition here where the contrast drops. And we identify this with the BKT transition, and I will explain later why this is what we expect. Okay, so in this first primary revival, you see that at low lattice depth, we have a very nice image. It looks really exactly like the actual image. But if you go to this deeper lattices, we get images like that, which actually look like laser speckles. And that, if you think about this, is also what we expect, because we have now interference between random phases. So we still have a BC on each lattice side, but now the phases of these individual BCs are randomized, and that is what gives rise to the speculite-like images. So this also confirms these interferences that you see here confirms this, and it does confirm that BCs on single sides. Is there a question?
No. All good.
Okay. Okay, good. Yeah, sorry. And basically, this is a way of measuring coherence. You see, the fact that we look at these revivals and whether they have a contrast or not is a way to measure the coherence in the system. But it's a way that is a bit indirect because this relies on the interference of many sides. So to evaluate that quantitatively is not so easy. So is there a way to better access the phase more directly? And the answer is yes, there is this phase microscope that we also realized and that I would like to explain you now. So the idea is also written down in this article by Selim Joachim and Panut Murthy, and it's basically a metawave version of phase contrast imaging. So where you have a phase, and by manipulating Fourier space, you map that onto an intensity. So say we have a wave function that has some phase fluctuations theta, and let's assume they are small, so I can also write them like this. So these are the phase fluctuations. The density is obvious from here, it's just constant. Yeah, it will have an envelope maybe, but the phase fluctuations, of course, don't appear if I just look at the density. But now, if I make a phase imprinting on the zero momentum component, yeah, so these fluctuations have all kinds of Fourier components, and this is basically my zero momentum component. I imprint a phase on that, and now these two terms, previously they were out of phase. Yeah, this is purely real, this is purely imaginary, so they don't interfere when you look at the density. Now they do interfere, and we now get a mapping of these phase fluctuations onto the density fluctuations with a conversion factor alpha that's given by the sign of this phase that we imprint. Okay, that is the idea here. And you can look at it like this. So we have this matter wave protocol where we do have access to Fourier space, and we could realize that just by imprinting a phase with a flash of a laser pulse, an off-resonant laser pulse at the right timing and the right position here in order to realize that. This whole thing also works in a lattice. If we start with a lattice, the math gets a bit more complicated. You find, again, the details in this article. So this conversion factor now contains the Bloch coefficients and also some phases that are shifted by a reciprocal lattice vector. But the idea stays the same, that we have this mapping with a conversion factor. Now, there is an important detail that I should tell you, which is that we do not do this imprinting at this right time and the right place, but instead we use the aberrations that we have anyway, and that has basically the same effect. So we make kind of a continuous phase imprinting here from the aberrations of the trap that we use onto this matter wave evolution. And to calculate it, so this is basically the fact that we don't have a harmonic trap, but the Gaussian beams that we use have some anharmonic part here. And we went through the whole math. It's a bit lengthy, but you find it in the supplementary of our article. And you can see that at this position in Fourier space, what happens here basically gives you a phase shift for each momentum, that's given by this formula. That is an effect of the aberrations, and it's pretty similar to the phase shift that you would do otherwise. So here's the phase as a function of momentum from 0 to 1 reciprocal lattice vector, and this pink line is basically the result from our calculation here, and the orange line is what you would ideally do if you imprinted it by hand, where you say I want to imprint a phase at zero momentum, of course, with a finite width. And what we get is just a smeared out version of that. But we get it for free, so we don't have to align any laser and hit it correctly. So we just get it for free. That's cool. And then you can calculate the conversion factor that depends on phi. It now also becomes somewhat momentum dependent, but you see that the momentum dependence is actually not very strong. So the purple line here is again this theory, so this analytic theory with a lot of approximations that we do, and the blue line are some numerical calculations that we did, and you see that there is basically a plateau here at the relevant momenta that actually are relevant for our phase fluctuations. So basically the assumption of working with effectively a constant conversion factor is justified here. And I will also show you that it works well, which kind of further strengthens that. So to estimate the conversion factor, we can, for once, look at our calculations for what kind of phase we do imprint with aberrations that we know, because we know what is the waist of the beam that tells us what is the strength of the quartic term and so on. And there we expect a conversion of factor of 0.43, but we also calibrate it directly via the thermal fluctuations and get a value that's quite close. And so we use this value in the following. So how do we do that? We use the fact that the variance of the on-site phase fluctuations should be given by T over J. So T is the temperature and J is the many-body tunnel coupling between the Josephson junctions. And so we evaluate this quantity and see that it actually follows a straight line. And this can be used to calibrate this conversion factor, to make it such that this relation is fulfilled. So this is the range of sites between 1 and 3 sites, like these distances. So the momenta that corresponds to these distances that we basically are mainly interested in. And over this range, this conversion factor is approximately constant. So I should mention that, of course, measuring phases is something that has been done before a lot. I mean, even one of the first experiments that people did with BC is looking at interference. And there's also experiments where people did, for example, a short expansion, where a phase gradient would then turn into a density gradient. That was, for example, is what you see here. But all of that basically is a compromise on resolution. So if you make an expansion, well, then you smear it out. So in our case, where we have this matter wave imaging condition and manipulate in Fourier space, we get this phase mapping with the full resolution of down to single lattice sites. And so I think that is a very important point. So let me tell you what we find if we do this. What kind of physics do we see in the lattice if we study the phases? So it is BKT physics that we see. First, let me remind you that we had this phase transition here at the certain lattice depth. So we use that. And that's what I wanted to show you. we have now this image branch, and now we only look along this image branch, okay? And look at the points that we see there. And this is original data here on top. And you see that at low lattices, low lattice depth, everything is nice and ordered, and then there are more and more fluctuations until it kind of eats away. And to analyze it, we first sum up what the signal per lattice side, which is what you see here. And then we, of course, we have many of these images. We look at the average envelope and subtract that, and then we get these kind of images, which are basically phase profiles now. Yeah, so red means positive phase and blue negative phase relative to the mean phase of this BEC. And you see that in this case here, you have basically a flat density profile. And then if you go hotter and hotter, you get more and more phase fluctuations. Here you see nicely some domains also of phases. Yeah, here's a blue domain and a red domain and so on. So this is exactly what we expect. And we can now evaluate that, of course, more quantitatively with the G1 functions, or the phase correlation functions, and see what they do. So we expect here a BKT transition that has been studied before, but actually only in one experiment. So although there's this nice mapping, it's well known that if you have a Josephson junction array with local phases theta and a tunnel coupling J, which is kind of 2 times the single particle tunneling rate times the atom number. And so in that case, it's also, we have an inhomogeneous system, so J is a bit spatially dependent, so we have to take that into account when evaluating it. But that this basically maps to a 2D Bose gas, if you like, or to a just classical XY model, where you expect a BKT transition. And it has been studied here in this experiment in the Cornell group in 2007, where people looked at the proliferation of vortices, and they imaged the vortices by mapping back from the lattice into a continuous system, then expanding and then identifying these holes here with the vortices. And they also stepped through the lattice depth to tune basically this phase transition. And what we expect is then quasi-long range order in this low temperature phase and exponentially decaying order in the high temperature phase. And we will mainly focus on this region now. And the good thing is that in the whole region, we have suppressed density fluctuations to be expected. And that's, of course, nice, because then we can attribute all the fluctuations we see to actual phase fluctuations in the original system that were then mapped to density fluctuations. And this is the result if we take our images and evaluate the G1 function, so the phase fluctuations. And we do that, this is a log-log plot, and you see it fits well with a linear fitting functions here, so an algebraic decay. And we have it here for different lattice depth, yeah, and so it decays faster if we get hotter. But all points are basically well described with a power law, which is what we expect here in this low temperature phase. And another prediction of BKT transition is that this exponent here that we fit here, so basically the slope of this curve, that it grows linearly with the temperature in units of J. And we do that and again look at it at different radii, different lattice depths and so on, and it all falls nicely on this one line. So nicely confirming this prediction, and also nicely confirming that our microscope is indeed working. Yeah, so it's also kind of a calibration of our microscope to find out these relations here, to reproduce them. But there's one point: our system is inhomogeneous; it's trapped, so we don't expect it to get the right numbers for this phase transition. So let me explain that to you. So normally you would expect that what we would call a critical exponent, so the exponent at the phase transition should be 1/4, so 0.25. That's what you expect in a homogeneous infinite system. So that is basically, remember, exponent grows from 0 to 0.25 at the phase transition, which is here marked by the gray line. So it's slightly below 0. And in our case, you see it's much larger. It's at 0.6 about. And this is due to the fact that we have this very inhomogeneous and small system. And also other experiments, there, as already mentioned, there's this, there are actually only 2 other experiments that did measure this exponent. This is one from Chris Foot in Oxford and one by Selim Jochim in Heidelberg. And they're given here basically, they found values between 0.17 and 1.4. So you see, the funny thing is, whatever you do with trapping, you still obtain an algebraic decay, but the exponents are renormalized. And there's also some theory that looked at this and also found that this is the case, that you will still get these algebraic decay. So that fits kind of with this expectation. Yeah, so we find BKT physics in these small trapped systems, and this validates the phase microscope. And so this is already the summary. So I talked about the matter wave Talbot carpet and the phase microscope with BKT physics. And of course, I don't know if I have time for this. Let me also do some outlook. So what we will work on next is a full-fledged phase microscope, where we now add some single atom imaging, as we discussed in the beginning of this talk, where we detect really each single atom in a strongly correlated regime. So far, we're working in a weakly in a regime of like many atoms per side of BECs, and that were weakly interacting. But the question is, what happens if you apply these kind of techniques to the strongly interacting regime? And another thing that we are looking at is a Talbot microscope. So I mentioned in the derivation of the microscope that we assume small phase fluctuations. And actually that is quite crucial, because what happens is actually the phase fluctuations are interfering with the residual BEC, with the atoms at momentum 0, where you imprint the phase. And this interferes with, and then you get the fluctuations. But this relies, of course, on the fact that you still have a BEC, so that the fluctuations are small, that they don't totally destroy it. Once they get too large, the thing breaks down. Yes, that's why we only evaluated the low temperature regime quantitatively. The fluctuations were still small. But we think that if we instead look at these Talbot copies, now without all this aberration stuff, just as the Talbot copies, that now it becomes more complicated, because the shapes that we see here are given by interference of all the neighboring sites. So it's more difficult to obtain, more involved analysis, but it should be more powerful in the sense that you could also reconstruct it for large fluctuations. And that's what we are currently working on to show that first theoretically and then also experimentally. Yeah, with that, let me thank the team. So this was done by the 2 postdocs by now. So they both graduated, Justus Brüggenjürgen and Mathis Fischer, who are now both finished. And Nikas Gaming is a machine learning guy in our team. And it was done in the institute with Klaus Senkstock. And as Peter already said, I just moved to the Technical University of Dortmund. And maybe I can use 3 minutes to make some advertisement for that. Yeah, thank you. So what are the plans there? We will look at stabilization using dissipation within this research unit here. So we will look at what happens if we have, say, gain and loss in our system, and what kind of states appear then. Can we use that to stabilize, for example, topological phases? That's one direction. The other is to push this whole idea of this matter wave microscope much further. So I showed you already that we can reach 100 nanometers. So this is the image I showed before. And that is already much better than the resolution that you have in a classical microscope, which is purely optical, where you're typically 800 nanometers or so and can just barely resolve the lattice sites. And if we push this idea here further, like keeping it at a magnification of 100, but then kind of removing all matter wave aberrations such that we can really fully exploit that, I think we should be able to push it to 4 nanometers only. And then we would see images like that if we load atoms into p bands or so of this honeycomb lattice. That's taken from this article where people looked at chiral superfluids of p bands in a honeycomb lattice. They looked at it in momentum space. This is just a simulation. But with this microscope, you would be able to directly take such images here experimentally and study the fact that these p orbitals here will have a chiral structure with a chiral phase pattern. So I think that would be really exciting to do that, and we will set up a new experiment in order to push it in that direction. And so maybe many people don't know where Dortmund is. So let me tell you, this is Europe, yeah? And some people define a blue banana in Europe. So I don't know if you have heard of that. That's basically the center of Europe. That's where all the economic activity is, yeah? And like right in the center of that is the Ruhr area, and right in the center of that is Dortmund. So although it's maybe a town that not everyone knows so well, it's actually in the center of everything, if you want to put it that way. Okay. And so if you like this kind of physics, maybe you would be interested in coming to Germany for a PhD or postdoc or so. I have positions available, and please just contact me. Yeah, this was it.
Thank you. Yeah, thank you, Christof, very much for this very nice talk and also the fascinating outlooks. It's really amazing if you can push it into a regime where you might see the, inside the lattice side, what the orbitals are. We've got time for questions. Michael.
So how do you turn off you get this phase imprinting because of the anharmonic components of your Gaussian beam. How do you turn those into the expansion phase? Is it just because you're expanding into a much weaker trap and so they're smaller?
Yes, indeed, we switch it off, the trap off completely. So we don't just, which works as well. Kind of, you still get an imaging condition if you just completely switch it off. And that's what we do. And then we don't have the aberrations. Yeah.
So just to clarify, for the procedure where you do the phase imaging, do you do something different than for the procedure where you just want to have the microscopic imaging? Just if you just want to the enlargement, is this a different procedure or?
Yeah. No, well, not really. Kind of, because it's a good point. These aberrations are hard to switch on or off. Yeah, that's kind of a drawback of it. So, and actually, we also plan to, in the next step, to make larger beam waves such that we can get rid of it and then introduce it at will with additional beams or so. That will, of course, be better. But for now, we just had it and used it as it is. So in that sense, it is one of these aberrations that would blur images as well. That's what I said. Kind of for this new experiment, we will, now that we understand it very well, get rid of all of that for the actual imaging. Yeah, in these very early experiments, in this first article, we froze out the coherence, and then such that we don't have phases anymore, such that there would not be such a mapping. So that would not have affected these earlier images.
Mm-hmm. Any further questions from the audience? I don't see any, and we are reaching the top of the hour. So thank you again very much, and for taking time in your evening. It was a very nice time. Thank you.
Yeah, thank you for having me. And hope to see you at DayMob or somewhere else again. Yeah?
Yep, thank you.